This is problem set 4, exercise 4. Here in this case, they tell us that we have an undirected connected tree of n vertices. Okay, so here we have that the number of nodes is n, and they tell us that there is a particular vertex in the tree which is going to be this one, which has degree k. Okay, so I'm going to call this node 0. This is going to be node 0. So the degree is going to be k. In this case, k is equal to 3, obviously, because we have 1, 2, and 3 links that are joined to this link. The point is that if I removed this node, then these three parts of the network would be disconnected. And they ask us what is the betweenness centrality of this vertex. So what is the thing? Well, there is an error here. Okay, this is the real formula. So the betweenness centrality of this node can be calculated as the following, because remember that the betweenness centrality of node 0 is going to be like the addition for every pair of nodes in the network where none of these nodes is equal to 0, okay, of the number of shortest paths that join these two nodes that go through node 0, and also the total number of shortest paths. Okay, so that's the idea. Now, in this case, it's quite obvious that I'm going to assume that I have these three elements. Okay, so this is, I think it's easier to understand this way. So if I have these three disconnected components when I remove this node, then it means that all the nodes, all the paths that are going to join, the shortest paths that join every node here with every node here, must go through this node. And also all the shortest paths that join these nodes here with these nodes here are going to go through this node. And again, the same for the other pair of nodes, of sets. Okay, so all the nodes in this set and all the nodes in this set, all the shortest paths that join these two nodes, okay, any node of these two networks, then is going to be go through this node. So the point is that if I take one node here, for instance, and one node here, okay, these two nodes are going to be the shortest path is going to go through node 0, okay, and this is if I pick this node and this other node. But if I pick any other node here, would be the same result. So the point is that they tell me that here I have n1, n2, and n3 nodes, okay, in each of these sets. So what is the total number of paths that are going to go through node 0? Okay, well, it's going to be, this is going to be, I'm going to do it in this example, in this particular example. It's going to be twice, because remember that it's going to be this summatory is for every pair of I and j. So that means that I'm going to count twice every node, because I'm going to count this one, but I am also going to count this one, okay, and the same goes for the denominator. So I'm going to count twice as much every pair. So we are going to have twice n1 times n2 shortest paths that go through node 0, plus twice n1 times n3 shortest paths that go through node 0, plus twice n2 times n3. Okay, and here, if you can see this, well, the total number of nodes, what is it? The total number of nodes in the network is going to be 1, which is node 0, plus n1, plus n2, plus n3. So if you compute n minus 1 squared, this is going to be n1 plus n2 plus n3 squared. And this, well, this is just the addition. Well, this is by definition this thing over here, and this is precisely when I is equal to j, I'm going to have the addition for all the, this is going to be n1 squared plus n2 squared plus n3 squared plus twice n1 and 2 plus twice n1 and 3 plus twice n2 and 3, which is precisely the amount that is the betweenness centrality. So the betweenness centrality of node 0 in this case is going to be n minus 1 squared minus the squares of all these nodes, okay? So this is basically this result. Again, Mr. Newman decided that instead of n minus 1, he preferred to write n. Okay, so far so good. The point is that this is explicit for 3 sets because this node has degree 3. But what happens if instead of degree 3, this node has a general case like what they say, degree k? So I have to generalize this expression basically. So what I'm going to find is that now the number of nodes is going to be 1 plus the addition from I equal to 1 to k of ni. Okay, and now n minus 1 squared, well, still we have the same, the expression here is going to be the same, okay? So here we have that the betweenness centrality is going to be, twice, or the addition for I, j different from I of ni and j. Okay, if I do it like this, or if I want to specify that we have then it's going to be from I equal to 1 to k, and the summatory from j equal to I plus 1 to k. Okay, this is 2k minus 1. Yes, of ni and j. This is the same way of writing the same addition because in this case, I'm adding up twice i's and j's, okay, because I'm not sorting I and j, but in this case I am sorting I and j. Here I'm saying that j is greater than I, so in this case I have that this is computed only once and not twice like in this case. So this is why I'm doing it like this. In this case this is not necessary really. So we are going to stick to this expression, and this expression is precisely if we do n minus 1 squared, this is the addition of I of ni squared. So this is by definition just what I told you before, okay? So this is going to be, on the one hand, the addition of the squares plus plus j of nij for j different from I. And sorry, this is an nj. And that's it. So here what we have is that this is n minus 1 squared minus this part here, minus this addition from I equal to 1 until k of ni squared. And this is the expression that they were asking us. So this is this expression here. And now we have to use this expression in order to find the betweenness centrality of the ith node of a line graph. So now the ith node of a line graph is going to be the following. So we have, this is going to be for answer of question B. Here we have the line graph. This is going to be node I, and this is going to be node N. Well, node N and lowercase n. And remember that I is not going to be in the bounds of this line because it doesn't make sense, okay? Because then it would be 0, the betweenness centrality. So in this case, what I have is that here I have n1 equal to I minus 1 nodes, and here I have a total number of n2 equal to n minus I nodes. So if I use this formula, okay, if I use this formula, then the betweenness centrality of node I is going to be equal to n minus 1. Well, now in this case we have, n1 and n. Yes. So we have that n minus 1 is going to be equal to n1 plus n2, just like before, okay? Because we are not considering node I. Node I, I'm not counting it in any of these two sets, nor in this set, not in this set, nor in this other one. So what I have is that xi is just twice n1 times n2. So we find that this is 2 times I minus 1 times n minus I. And this is the final result, okay? So the end is that this is the result that they're asking us. This is the betweenness centrality. This is the number of shortest paths that go through node I.